Hello and welcome to this lecture on advanced electric drives. In the last lecture we are discussing about the sinusoidally excited permanent magnet synchronous motor, or in brief we call this motor to be PMSM. In a PMSM motor, the windings are distributed sinusoidally and the back EMFs are also sinusoidal. And when we see the equivalent circuit that we have seen in the last lecture, the equivalent circuit consists of a current source here in the stator. We can excite the stator from a current source for better control of the torque. Torque is usually controlled by MMF and MMF is obtained by a current. So, if we can excite the stator by a current source, the torque can be very easily controlled, and the rotor is a permanent magnet which is represented as IF, and XS is the synchronous reactance, and IM is the resultant of IS, the stator current, and IF, the field current. Now, if we see the phasor diagram, in the phasor diagram we see that the field is along the d axis. So, this is our d axis, and the field induced EMF is along the q axis. And we can say that the magnetizing current is the result of the field current and the stator current. So, we can say here that I m, the magnetization current, is equal to the phasor sum of I s and I f. I s is the stator current and I f is the field current, and this I m, the magnetization current, is responsible for the voltage in the armature. So, we can see that V, the voltage vector, is shifted from I m by pi by 2. So, in fact, this angle is also pi by 2. So, we have considered a machine, PMSM machine, where we have ignored the resistance in the stator. The stator does not have any resistance. You can see that we just have the synchronous reactance, that is XS, and the core loss, the friction loss are neglected. So, we have a situation where the losses are neglected. We have a machine with only synchronous reactance. So, if we find out the power P in, the power input is same as the power output, because we do not have any losses, and that is equal to EF, the field induced EMF, the stator current IS, this is the field induced EMF EF, the stator current is IS, and angle between EF and IS, that is delta prime minus pi by 2. And if we simplify that, what we obtain here is 3 XS IF IS sin delta prime. So, in fact, what we see here, that the power is proportional to sine of delta prime. So, if we change delta prime, the power will change. What is the torque? Torque is power by the mechanical speed. So, we can find out the torque in the following fashion, that the torque is equal to P out by the mechanical speed, and the mechanical speed is omega r m. If we divide this, what we get an expression that is k, a constant, into IF into IS into sine of delta prime. So, it means the torque is still proportional to sine of delta prime, and also it is proportional to IF and also IS. IF is the field current. Of course, we do not have any field winding here. We are talking about a permanent magnet synchronous motor where the field is a permanent magnet. The stator is a current fed system. We are feeding the stator from a CSI or a current controlled VSI. So, we are basically controlling the stator current, that is IS. So, by controlling the stator current, we can control the torque. Now, what is the condition for maximum torque per ampere? So, if we want to have the maximum torque per ampere, we have to make delta prime equal to plus or minus pi by 2. So, it means delta prime or sine of delta prime should be the maximum value, that is plus 1 for motoring and minus 1 for braking. So, in fact, we can make this delta prime, which is something like a torque angle, plus pi by 2 for motoring, in which case sine delta prime will be 1, and we can make delta prime minus pi by 2, in which case sine of delta prime will be minus 1. So, if we make delta prime is pi by 2 here, for motoring, let us say, in that case this is the angle between IF and IS, that is delta prime, and that is equal to pi by 2. And we see here that the voltage V is here, and we have the field current, and IS is the armature current, and the torque is given by Kf into Is for delta prime is equal to plus minus pi by 2. And this for the braking operation, when we make delta prime is minus pi by 2, this is again the delta prime, and this angle is minus pi by 2, in which case Is is lagging behind If by pi by 2. So, in that case the torque will be negative, as you already seen here, T is equal to plus minus Kf into Is. So, for delta prime minus pi by 2, T is equal to minus Kf into Is. So, T in this case is minus Kf into Is, and that is for the braking operation. So, when the motor is braking, the torque has to be negative, because the motor kinetic energy has to be brought out from the mechanical part and has to be converted into some equivalent electrical energy. So, during the braking, motor is in fact operating as a generator in which torque is negative, and that is reflected in a phase current. The phase of this Is is shifted by pi from the usual motoring position. For the motoring, Is is in phase with Ef, this is for the motoring, and for the braking, this current Is will be pi by 2 shifted from the original position, and it means the energy is fed back to the source. The motor is behaving as a generator. Now, in some application we want higher speed. If we want higher speed, we need to have flux weakening. By flux weakening, we mean the air gap flux is reduced. Now, in this case we are having a permanent magnet, the rotor is a permanent magnet. How to reduce the air gap flux? The magnet strength cannot be changed, the magnet is inside the rotor, the strength is fixed. So, we can reduce the air gap flux by having a negative current component along the field axis, and that is obtained by increasing or having a large delta prime angle. So, if we make this angle quite large, this is the angle which is delta prime, and when this is made large, Is has got two components, one is Ix x and Isy, and Isx is along Ef, or it is in the q axis. This is the q axis, and this axis is the d axis. So, this Isx is along the q axis and it is cross magnetizing. This does not increase or decrease the field current or field flux. Now, Is also has a component, that is Isy, which is demagnetizing, because this Isy is opposing If. So, when this Isy is opposing If, the equivalent field current is reduced. In fact, Im is reduced here, and we are talking about the field weakening condition, and Im is equal to the stator current plus the field current, and we see that the stator current has a component, that is ISX plus ISY plus IF, and ISY is opposing IF. Now, this is reduced. So, since this is reduced, we will have a reduced IM, and once the IM or the magnetization current is reduced, even with the increased speed, the terminal voltage will be constant. So, this is called field weakening, and the field weakening is preferred for higher speed. When we want to have higher speed operation, we have to reduce the magnetization current, which is achieved by increasing delta prime. Now, we can have some advanced control in PMSM machines. The advanced control in PMSM, one of the advanced control is called a vector control of PMSM. So, we will be discussing about vector control of permanent magnet synchronous motor. So, when we talk about the vector control, we need to understand the model, the actual model of the machine, because vector control improves both the transient and the steady state response. In case of a PMSM, the model of the machine is somewhat similar to that of a synchronous machine, but having some difference in the sense that a PMSM does not have a wound field in the rotor and also does not have the dampers in the rotor. So, the equations are derived in the rotor reference frame. So, in this case what we do here, we take a rotor reference frame and we derive the model of PMSM in rotor reference frame. So, in this case we have a 2 axis model. The machine is running at a speed that is equal to omega r. So, we can write down the equation in the stator d axis and the stator q axis. The rotor in this case is a permanent magnet. So, we have a north pole here and we have a south pole here. This is our d axis and orthogonal axis is the q axis. So, we have the d axis winding here and we have the q axis winding here. Stator, the rotor in this case is a permanent magnet. We have a north pole and we have a south pole, and in the rotor we do not have any winding, and since we do not have any winding in the rotor, we cannot write equation for the rotor. So, we will only write down the equation for the stator. In the stator we have 2 windings, ds and qs. So, this we call to be VDS, and since we are talking about the rotor reference frame, we can choose to give a superscript, that is R here, and this is VQS with the superscript, that is R, and here we have a current that is IDS R, and here we have a current that is IQS R, and this axis is rotating at a speed of omega r. The rotational speed in this case is omega r, is rotating in the anticlockwise direction, and the speed is omega r. So, we can write down the equations. VDS is equal to IDS into RD, the resistance in the D axis. This winding can have resistance that is equal to RD. This winding can have resistance that is equal to RQ plus P psi ds, the flux linkage in the D axis stator in the rotor reference frame. And again, since the reference frame is rotating with rotor speed, there will be rotationally induced EMF in the stator. So, that can be written like minus of omega r psi q r psi q s in the rotor reference frame. And similarly, we can write down for the q axis VQS is equal to IQS RQ plus P psi QS plus omega r psi ds. Now, what is psi QS and what is psi ds? Psi ds is given as the flux linkage in the D axis stator, that is LDS into IDS plus psi FR. So, we are talking about the rotor reference frame, we can give the superscript R. Now, in this case the LDS is the D axis inductance of the stator. Similarly, we can have the flux linkage for Q axis. The flux linkage for Q axis psi QS is given as LQS into IQS R. In the Q axis there is no magnet, it is iron. In the D axis we have the magnet, these are the magnets. So, we have magnet in the D axis, and in the Q axis there is no magnet. So, in fact, in a PMSM machine the D axis inductance is smaller than the Q axis inductance. So, in general we can say that LDS is less than LQS, because if you see in the D axis we have a magnet. So, the D axis in this case we have magnet, and the magnet will behave like a air gap. So, the D axis permeance is reduced and hence the D axis inductance is less. On the other hand, in the Q axis we have no magnet in the Q axis. In the Q axis we have only iron and air gap. So, the Q axis permeance is more and hence the Q axis inductance is more. It is opposite to a normal synchronous machine where we have LDS higher than LQS. In a permanent magnet synchronous motor, LDS is lower than LQS. So, we have this inequality here that LDS is the D axis stator inductance is lower than the Q axis stator inductance. So, we have this equation for the flux linkage. Now, we can replace the flux linkage in this equation. We can call equation number 1 and equation number 2. Now, these two equations have the flux linkages, that is psi ds, psi qs. So, we will be replacing the flux linkage by their expression and rewrite the final equations. So, if we do that and write down the final voltage equation, we will find it or represent this in a matrix form like this: VDS, VQS, the rotor reference frame, that is equal to we can have this current expressions here, that is IDS is the D axis current in the rotor reference frame, IQS is the Q axis current in the rotor reference frame. And what about this matrix? The the matrix we have R d here plus L d s p, and in this case we have minus omega r L q s. Similarly, this element would be L q plus R q plus L q s p, and this element will be plus omega r L d s. And we have also induced EMF because of the field. So, field induced EMF will be in the q axis. So, this is 0, and what we have here is omega r into psi f r. So, this is the equation of a PMSM in rotor reference frame. So, we can replace this psi f r. Psi f r is the field flux. What is field here? Field is a permanent magnet. We can represent this equivalently by means of a current, and that current is I f r. So, we can say that psi f r is equal to L m into I f r, or L m d into I f r. So, this is the model of the PMSM in rotor reference frame. Now, the next equation is the torque equation. So, we can also write down the equation for the torque. The torque equation is given by this: T e is the torque is equal to 3 by 2 into P by 2. So, if we remember the expression for the torque of a synchronous machine, PMSM is nothing but a synchronous machine. The only thing is that the rotor has been replaced by a permanent magnet. So, in that case we will see that the equations are psi d s I q s minus psi q s into I d s. So, we will be replacing all these expressions in this equation. So, 3 by 2 into P by 2. What is psi d s? Psi d s is given as L d s into I d s plus, we have the expression in this case L m d into I f r into I q s. We can say I f r in the rotor reference frame into I q s minus psi q s into I d s. What is psi q s? Psi q s is L q s into I q s into I d s. That is the expression. The damper windings are not present. We are talking about a permanent magnet rotor in which there is no damper winding. So, this is the expression for the torque. Now, we can rearrange this expression. So, if we rearrange this, what we obtain is the following. We get here 3 by 2 into P by 2. So, we have one term which will contain L d s minus L q s, and then I d s into I q s plus L m d into I f r, the rotor reference frame, into I q s in the rotor reference frame. So, this is the expression for the torque in a permanent magnet synchronous motor. Now, we see that the first part here is proportional to I q s and I d s, no doubt, but it is also proportional to L d s minus L q s. The first part of this equation, right hand side, is called the reluctance torque. So, this torque is called the reluctance torque. Because it is present due to the reluctance variation in the d axis and a q axis. And what about the next part? This next part is called the field torque. This is present because of the field winding equivalent current, that is IFR. IFR is the equivalent current of the field winding because of the permanent magnet. So, this is the equation for the torque. Now, we will implement vector control. In vector control, what we do, we try to independently control the torque and the flux, just like a DC machine. So, vector control of a permanent magnet synchronous motor aims at control of the torque and flux independently, just like a DC machine. So, in this case we can just go back to our phasor diagram. So, in the phasor diagram what we saw there, that we have the field current, and we have, this is the d axis, and we have the q axis, and we have the current. In this case the stator current can be in any arbitrary direction. We can say, suppose this is the current of the stator, which is here Is, is a vector, and we have If. So, we can resolve this Is into two components. So, we can have a component along the q axis, and we can have a component along the d axis. So, this component we can call, let us say this is called If, It here, and this component we call If. So, we can resolve the stator current, that is Is, into two components. One is It along the q axis and If along the d axis. So, this is our torque angle that we were discussing, that this is basically our delta prime. So, we know that torque is proportional to sine of delta, and we have these two currents. So, what we can do here is that we can say that It is equal to Is into sine of delta prime, and that is also equal to Iqs in the rotor reference frame, because this is the q axis component of the current. So, that also we can say that is equal to Iqs, and If we can also write that If is same as Ids, the d axis component of the stator current. So, we can say that It in this case very clearly we can say It is equal to Iqs, that is equal to Is into sine delta prime. Sine of this is It, and If is equal to Is into cos delta prime. This is the angle delta prime, and the component of Is along d axis is the Ids, that is equal to Ids. So, if we replace this expression for Ids and Iqs in the torque expression, we have the following expression, that Te is equal to 3 by 2 into P by 2 into LDS minus LQs into Is square sin delta prime into cos delta prime, that is a reluctance torque part, Is square into sin delta prime into cos delta prime, plus LMD into IFR into Is into sine of delta prime. Now, we can further simplify this, that is equal to 3 by 2 into P by 2 into half of LDS minus LQS into I s square into sine 2 delta prime plus LMD IFR in the rotor reference frame into I s into sine of delta prime. So, this is the equation for the torque. Now, what we do here, we put delta prime equal to pi by 2. Now, if we put delta prime equal to pi by 2, that is the condition for vector control. So, vector control means we are trying to control the PMSM just like a DC machine, and that is achieved when we make delta prime equal to pi by 2. So, if we make delta prime equal to pi by 2, we can have this expression for the torque T is equal to 3 by 2 into P by 2. So, if we see the first expression, that is sine of 2 delta prime. So, if delta prime is pi by 2, 2 delta prime is pi. So, sine of pi is equal to 0. So, the first term will be 0, this term vanishes, the second term will be present, and we have made here delta prime is equal to pi by 2. So, we have got LMD IFR into I s. So, what we obtain here is LMD IFR into I s. So, this resembles like a DC machine. So, in this case we can obtain the maximum torque per ampere because delta prime has been made equal to pi by 2 and the expression looks like that of a DC machine. So, in general we can say that IAS has got two components. IAS has got a component along the field axis, that is called the flux component of current, and there is another component which is orthogonal to the field axis, that is in the Q axis, that is called the torque component of current. So, in general we can say that IS, if it is a phasor, will have IF is along the field axis or the D axis, and there is another component which is along the Q axis, that is called IT. So, we can say that IF is called the stator flux component of current, and IT is called the stator torque component of current. Usually in a permanent magnet synchronous motor, the flux is produced by the field winding, the field magnet. So, the field magnet is producing the flux, but the flux can also be controlled from the stator side. So, the flux can be controlled from the stator side by controlling IF, and that is why it is called the flux component of current. And the torque is usually controlled by controlling IT, and that is why this is called the torque component of current. So, in general we can have a block diagram, and the block diagram will explain the various control aspect of the vector control of PMSM drive. So, what we have here is closed loop control block diagram for vector control of a permanent magnet synchronous motor drive. So, in this case we start with the speed controller. We want to control the speed of the machine. So, we have a reference speed and we compare that with the actual speed. So, we start with the speed controller. This is the reference speed omega r m, and we compare that with the actual speed, that is omega r m, and what we have here is a PI controller. This PI controller will be giving us the magnitude of the torque. So, we can say this is the torque that we get out of it, and the torque will be controlled as per the speed. As we know that up to the base speed the torque will be constant, and after the base speed the torque will be reduced for the field weakening region. So, we multiply this with a factor that is coming from the field weakening performance, and then what we obtain here is the reference torque T e, and the reference torque is divided by a constant to give us the torque component of current. Similarly, the flux component is obtained as follows. The flux component is obtained by a function generator. This is a function generator we have, and from this we feed it to the function generator, and the function generator we can call this to be function of f of omega r m here, and this output goes to this particular block, and then this is multiplied by a constant, that is K f, to give us the magnetizing flux. And the magnetizing flux is used in a function block to give us I f. I f is the flux component of current. So, we have I t here, the torque component of current, and we also have I f, the flux component of current, and when we transform this to current, we get the currents in phase A, phase B, and phase C of the stator. So, we were discussing the block diagram of the closed loop speed control of a permanent magnet synchronous motor under vector control. So, we have the torque component of current, that is I t, and the flux component of current, that is I f. We can convert this into the polar components, one amplitude and a phase angle. So, these are the two components of current. So, we have magnitude and angle resolver, magnitude and angle resolver. So, with this, what we do here, we convert this, the torque and the flux component, into a magnitude and a phase angle, and the magnitude here will be the magnitude of the stator current, that is I s. I s star is the reference stator current, and the phase angle, is, in this case, is delta prime, and we add here with this delta prime the rotor angle. We have a summer in this case, we add in this case the angle of the rotor, that is theta r, and this is called the theta s, and we can feed this to a stator current reference generator, stator current generator. So, we have the stator currents here I a IBS and ICS, and these are the reference currents of the stator. And this IAS, IBS and ICS has to be impressed onto the machine. So, we have one inverter, and the inverter is operated with current control. So, in fact, what we are trying to do, we are trying to control the current of the stator by having a current control inverter. So, we have the PMSM machine here, and this is fed from a 3-phase inverter with its control. So, 3-phase VSI with control, and we are feeding the stator of the PMSM drive, and this is of course is fed from a DC link. So, we have a DC power supply here, VD, and this is we have phase A, phase B and phase C. So, we can sense the various currents here, IA, IB and IC, or IAS, IBS and ICS for the stator, and these currents are compared with their reference value. So, we have a comparator here. So, this is IAS. Similarly, here we have IBS, and here we have ICS, and this comparator will be giving us an error, and the error is processed through usually hysteresis controller for control of the inverter. So, we can have a current control mechanism here, and one of the popular mechanism of current control is hysteresis current control, in which we can have the hysteresis control after this comparator block. For the 3 phases, we can have 3 hysteresis controller, and this will be giving the signals for the inverter. So, we can say this is inverter gate drive signal. So, this is how we can generate the signal to the gates of the transistor or IGBTs of the inverter. Now, to control this, we need to have the position feedback. In fact, all synchronous machine will require position feedback for the closed loop control. So, we have an encoder in the rotor mounted on the rotor shaft, which will measure the position, and this position will be used for control of the inverter. So, we have the position sensor here. It's encoder, rotor position encoder, and what we obtain out of this is the mechanical position, that is theta Rm, that is multiplied by the pole pair to give us the actual rotor position in electrical angle. Theta R is the electrical and theta Rm is mechanical, and the position is processed through another computational block to find out the speed. So, we have here the speed calculator, to which we feed this theta Rm, and after that what we are obtaining out of this is the mechanical speed of the rotor, that is omega Rm, and the same speed is fed back here. So, we have the mechanical speed which is calculated by the speed calculator, and it is fed back and compared with the actual the reference speed, and then we have the speed controller. So, this PI controller that is used here is the speed controller. Now, we have the various blocks. Important aspect to understand here is that this block diagram can control the speed below the base speed and above the base speed. Below the base speed, the magnetizing flux is constant. So, if we see this function block, this is the functional block that we have added here. This functional block has a typical characteristics. Up to the base speed, the flux remains constant. So, this basically gives us psi m versus omega r m. The x axis is omega r m and the y axis is psi m. Now, what is psi m? Psi m is the magnetizing flux, which is the resultant of the field and the stator. Now, let us see what is psi m. Now, we have already seen that we have psi ds, the d axis stator, and we have the d axis rotor, that is the field, and we have the q axis stator, that is qs. So, in fact, if we draw the equivalent circuit will look like this. In the d axis we have the resistance here, we have a back EMF, we have the leakage inductance, and then we have the magnetizing inductance, and here the circuit is complete. Now, this we are applying here is VDS, the applied voltage, and this is our RD, is the resistance of the stator, and this is LMD, is the magnetizing inductance in the d axis, and the permanent magnet is represented by a current component, and this current component we call IFR, and in the rotor reference frame. All the variables here are in the rotor reference frame, we denote them by a superscript r. This is the leakage LLA, and the d axis inductance usually is LDS that we refer, that is the sum of the leakage inductance plus the d axis magnetizing inductance, that is LMD. Similarly, in the q axis we have the resistance, we have a rotationally induced EMF, and then we have a leakage, and we have a magnetizing branch, and here this magnetizing branch is LMQ, which is the q axis magnetizing inductance, and LLA is the leakage of the stator, and RQ is the resistance of the winding in the q axis, and this applied voltage is VQS, referred in the rotor reference frame. So, that is superscript is R. So, this is the direction here of the voltage. If we have a reference like this, we can have plus minus sign, and then the back EMF in this case is omega r into psi qs. This will be helping the applied voltage. It is minus and plus here, just like a synchronous machine, and here the back EMF will be plus and minus, it is omega r into psi ds. So, we have three different fluxes. The flux is psi ds is this flux, and psi qs is this flux. So, if we see psi ds in this case and psi qs, we can express the magnetizing flux in the following expression. So, we can say here that psi m is nothing but psi ds square plus psi qs square, the total flux linkage, and that is equal to LDS into IDS plus we can say psi FR. Psi FR is equal to LMD into IFR. So, this is psi FR, the square plus psi QS is LQS into IQS square. So, this is what we have here, and then this is the magnetizing flux or the total stator flux, which has got the D component and the Q component. So, we can also call this to be the total stator flux linkage. So, this is also called the total stator flux linkage. And if we want to know what is psi m, we have to have the idea of IDS, idea of IQS, also the magnet strength, that is psi FR. Now, from this we can calculate what is psi m, and actually psi m is constant up to the base speed. So, we have a function generator, and the function generator gives us the variation of psi m with the speed. So, this is how it varies. So, we have psi m in the y axis. So, psi m remains constant up to the base speed, and after that this enters into the field weakening mode. In the y axis we have psi m, in the x axis we have the rotor speed omega r m. So, omega r m is in the x axis. So, as the speed increases up to the base speed, we have got this omega r b, the flux remains constant, and then after this omega r b flux decreases. So, in fact, what we can say here, this is the field weakening. And this correspond to constant flux operation. And this function we can say this is 1 per unit, and then this decreases. So, the functional block that we have mentioned here, this particular block f of omega r m, we can say that f of omega r m is equal to 1 for speed omega r, magnitude of this is less than omega r m, here is omega r or omega base, omega r m base. So, if omega r m is less than omega r m base, this function is equal to 1, and that is equal to omega r m by omega r m base for speed omega r m higher than omega r m base. So, this is the functional block here, and this functional block has got amplitude equal to 1 for the speed less than the base speed, and if the speed increases beyond base speed, we have a need of flux weakening, and the flux weakening is achieved by making this particular function less than 1. So, that is the functional block, and then we multiply by a scaling constant, that is k f. What we obtain is the total flux, that is psi m, and from the psi m we get what is I f. I f is the flux component of current. So, we know the torque component from the speed controller and from the torque I t, and we get the flux component from the functional block depending upon the speed, and then when we transform this into the polar coordinate I s and delta prime, we can find out the reference current for phase A, phase B and phase C. In the next lecture, we will be discussing more about this closed loop block diagram and closed loop speed control of permanent magnet synchronous motor, and we see that how the synchronous motor is operated below the base speed in constant flux operation and above the base speed in flux weakening operation.